Now let us draw a circle and mark a chord AB. This chord may or may not pass through the center. It's not important. What's important is the next property which we are going to look at. Mark any point on the arc of any segment. Let's say we mark point C on the arc of the minor segment. Then we form angle ACB by joining AC and CB. Now let's mark point D anywhere on the same arc, which will form angle ADB. Remember, we are marking random points on the arc of the same segment. Say we choose another point E on the arc of the same segment and mark angle AEB. Why are we doing all this? It's to appreciate the beauty of the angles contained in the same segment. Each of these angles is contained within the minor segment. But what's so unique about them? All the angles contained in the same segment are always equal. In this case, angle ACB is equal to angle ADB, which is equal to angle AEB. No matter where the point lies on the arc, the measures of the angles formed will always be equal. So what is the angle of a segment? Look at this figure. Chord AB has divided the circle into two segments. Segment AXB, which contains arc AXB, and segment AYB, which contains the arc AYB. What is the angle of a segment? For instance, what is the angle of the segment AXB? To find the angle of the segment, all we need to do is mark any point on the arc of that segment and join the endpoints of the chord to it. So to find the angle of segment AXB, we can mark a point C like this, join AC and CB to get angle ACB. Angle ACB is the angle of segment AXB. C, in this case, is called the vertex of the angle ACB. The vertex has to lie on the arc of the segment we are looking at. And as we saw, it doesn't matter where the vertex lies on the arc. The measure of the angle will always be the same. Similarly, to find the angle of segment AYB, we mark a point D anywhere on the arc AYB and form angle ADB. And this becomes the angle of segment AYB.